Here we are, students. This is the third part of this unit. And as you have noticed, if you look at your PowerPoint notes, is we skipped a few topics. I'm going to let you read about those on your own, hydrates and the nomenclature of acids. When you download the study guide for our first exam, you will see what is it exactly that I need you to know about these things. Hydrates, you just need to be able to recognize it from a formula what kind of a compound a hydrate is. And in terms of acids, we're going to be doing a whole section on that in lab, and we're going to study acid-base reactions in Unit 4 and forward. So we're going to leave that for later, okay? So we're going to skip these topics. Our concern now is with a subject called molar mass. Remember what we said before. What we can measure in the lab with high accuracy is the mass of a sample. But at some point, we'd like to be able to connect what we can measure with the way that sample exists, which is in the form of atoms, or in the case of compounds, as molecules or ionic, crystal lattices. So let's talk about something called the molecular mass or molecular weight. This is the sum of the atomic masses in AMU in a molecule. Let's consider sulfur dioxide. And here's a representation of it. And again, what we'll do is we're going to go to the periodic table and we'll look at the elements that make up this compound, right? So we have oxygen and we have sulfur, and we're going to look at the atomic masses of each. So 16 for oxygen, 32.07 for sulfur. Okay, so let me erase these things here. And let's go ahead and go forward. So we have one sulfur atom at 32.07 AMUs each, and we have two oxygen atoms at 16.00 AMUs each. We add that up and we arrive at what we call the molecular weight or molecular mass of this compound, 64.07 AMUs. In other words, if I could actually weight one molecule of SO2, it would weight 64.07 atomic mass units total. But just like we did with elements, for any molecule, the molecular mass or molecular weight in AMUs per molecule is the same as what we're going to call the molar mass, the grams per mole of molecules of this compound. So one molecule of SO2 would weight 64.07 AMUs. 1 mole of SO2 would weight 64.07 grams, and now we are in a territory that we can measure in our lab. Now, what about ionic compounds? In ionic compounds, because the actual number of atoms depends on the size of the sample, what we'll talk about is we'll essentially simplify the formula to the simplest unit, the formula unit, and we'll calculate what we call the formula mass or the formula weight. It's the sum of the atomic masses in one formula unit of the ionic compound. So if we have NaCl, again, remember the actual number of atoms depends on the size of the sample. But if we simplify everything to its formula unit, one sodium for every chlorine, we can find on the periodic table one sodium, 22.99 AMUs, one chlorine is 35.45 AMUs, for a total of 58.44 AMUs. This would be the formula weight or formula mass of a single unit of NaCl. But once more, for an ionic compound, the formula mass or formula weight in AMUs per unit is the same numerically as the molar mass, the grams in 1 mole. So 1 unit of NaCl is 58.44 AMUs. 1 mole of NaCl is 58.44 grams. Okay, let's do a practice here. What would be the mass of 2.50 moles of chloroform? And there's the compound formula. Notice that chloroform is not a binary compound, so we don't name it using the systematic rules we discussed in the previous section. So we're going to start by calculating the molecular weight of chloroform. That is the weight of one molecule of CHCl3. Please have your periodic table ready so we can fill these out. So carbon is 12.01 and there's one atom. Hydrogen has one atom at 1.01 AMUs each. And we have 3 chlorines at 35.45 AMUs each. And that's the total. We add it all up and we get 119.37 AMUs. So this would be the molecular weight or the molecular mass of chloroform. 119.37 atomic mass units per molecule. But the question is, how much is 2.50 moles? What is the mass of that? So we're going to use the molecular weight as a conversion factor. So we have 2.50 moles times what we determined from the previous calculation from the molecular weight, 119.37 AMUs per molecule is the same as 119.37 grams per mole of molecules. And as we've done previously, we set up the conversion factor so that the moles will cancel out. And now we have our final result, 298 grams to the proper number of significant figures. Okay, so hopefully that's a good illustration there. Now, we can go one step further. We can actually calculate, well, what about the numbers of molecules? Again, if we want the number of molecules starting from the mass, we can use the following flowchart. We just started with the mass in our sample. Then we have the molar mass conversion factor in here. And then we have Avogadro's number added to that. Just remember, I think that we would prefer in most of our calculations to go with 6.022 times 10 to the 23rd. And I can't believe I was able to write that on the screen. Usually it doesn't come out very good. Okay, so remember, this is something I borrowed from just a little image, but we would like to use the 6.022 times 10 to the 23rd version of Avogadro's number. Okay, so we've talked about chemical formulas so far, and we've said, well, a chemical formula reflects the composition of a compound. It tells me what elements are there and in what proportions, right? And we have used these to express composition, but where do these formulas come from? Because we cannot directly count atoms or ions. What we can do, however, is to measure the mass of each element in a sample of a compound by using appropriate analytical techniques. Now, when I say appropriate analytical techniques, it's deliberately vague in there because there are many techniques for determining what is a compound made of. The important thing is we're going to arrive at an expression of composition that will be the same for any sample of the compound. One way of arriving at a formula is to derive the empirical formula. This is the simplest whole number ratio of the atoms of each element in the compound. This is typically the formula that we can arrive at when we do chemical analysis of the compound. Now, the molecular formula, on the other hand, gives us the exact number of atoms of each element in the compound. For a molecular compound, the molecular formula may be the same as the empirical formula, or it may be a multiple of it. The chemical formulas of ionic compounds, though, are always empirical because remember, by definition, the formula of an ionic compound is the simplest whole number ratio of the atoms, or in this case, the ions, in the compound. Let me show you how this works. Here are two structural representations. This is what we call the space-filling models of two compounds. Notice that they are different compounds. They have different numbers of carbons and hydrogen atoms. However, if you were to simplify each one of these formulas to the smallest whole number ratios, what would be the empirical formula? Correct. Both of these compounds have a 1-to-1 ratio of carbon to hydrogen. So both of them, although they're different compounds, they have the same empirical formula. Let me show you the next one here. And I apologize, this may not have made it to your slideshow because typically in a classroom environment, I would be doing this one on the whiteboard. But you can write it down there on the side. What would be the empirical formula for each one of these compounds? The first was a little tricky. Notice the way it was written. We'll learn later on that sometimes scientists, chemists like to write formulas in a way that sort of suggests what the actual structure of the molecule is. But we'll tackle this a little bit later on. So the important thing here is how many carbons, how many hydrogens, how many oxygens. Okay, 2 carbons, 2 oxygens, 4 hydrogens. Since those are all even numbers, we can divide them by 2 and arrive at what would be the empirical formula, CH2O. I wrote it that way because that's the standard way that many of these compounds between carbon, hydrogen, and oxygen are written. Of course, you could have written it H2CO or, COH2. It doesn't matter at this point how you write it. Next one, P4O6. Okay, 4 and 6 would not be the simplest ratio between these because you can divide both of them by 2 and arrive at the empirical formula. All right, yes, P2O3. Very good. Good job. Okay, so you get the idea that for molecular compounds in particular, a given compound may have a molecular formula that is a multiple of its empirical formula. However, when we study compounds that we obtain from the field or from a sample somewhere, what we can do is analyze it, and what we're going to end up with is actually the empirical formula. The first step of this is to establish what is the composition, right? A convenient method for expressing composition is what we call the percent composition by mass, which is sometimes called also the mass percent or the percent mass. There's several ways that people say this. So for any element in a compound, I'm going to use the abbreviation E here as a generic symbol. The percent composition by mass, or the percent mass, is given by this equation. You divide the mass of element by the mass of that sample times 100%. So let's do a little practice here. We're trying to describe the composition of a compound where all we know is what it's made of, and all we know is what is the mass of each element in a given sample of that particular compound. Okay, I'm showing you here a picture of a mineral called chalcopyrite. It is one of several copper minerals. So we have an 8.33 gram sample, and it was determined by methods that we're not going to discuss here, but you will get to do a little practice in your lab next time. We have 2.88 grams of copper, 2.54 grams of iron, and 2.91 grams of sulfur. What is the mass percent of each element in this compound? Okay, don't forget, our formula here is mass percent is mass of the element divided by the mass of the entire compound, in this case, actually the sample, times 100%. Okay, to solve this problem, we're going to go to our paperboard here, and then we'll come back to the slideshow.
Okay, we are going to see how to solve this problem. Our goal is to find what is the percent composition of this compound according to the sample that we're studying. So the first thing I'm going to do is let me write down what are the elements involved. So we have copper, and we have iron, and we have sulfur. And it's telling us here how many grams of each we have in the sample. So our percent is going to be the mass of element divided by the mass of the entire compound. So for copper, that would be 2.88 grams. in a total of 8.33 grams of our sample times 100%. For iron, it would be 2.54 grams and 8.33 grams total times 100%. And for sulfur, it would be 2.91 in 8.33 times 100%. So let's see what these numbers add up to. I'm going to go ahead and do it here on my little kind of like little calculator here. It's not very high tech, but it works. So let's do copper first. 2.88 divided by 8.33 times 100, and that gives me 34.5738 blah blah blah. Now remember, the data that they gave us only is good to 3 sig figs, which means I need to round this value here to 3 sig figs. So the 3, the 4, the 0.5, and then the next digit has to be dropped, but since it's bigger than 5, I'm going to round up, and this is going to be 34.6%. What about this number here? Now, the times 100 is essentially a way of moving the decimal place. It has no bearing on sig figs. As happens in most occasions, your sig figs tend to be driven by the precision of the data that you are given. Okay, so let's do the next one then. All right, 2.54 divided by 8.33 times 100 equals 30.49 something, but we're going to leave it there. So we have to leave it to 30.5%, only 3 sig figs allowed. And the last one that we have is the sulfur. 2.91 divided by 8.33 times 100, 34.93, but we're going to have to leave that at 1 decimal because that gives us the full set of 3 sig figs. Now, one thing you want to do when you finish and before you wrap things up is to make sure all of your percentages should add up to 100%. Now, because you rounded, you may actually lose a decimal here or there. But I think in this case, you can see, actually, you can probably see it in your own hand. You don't have to do the calculator for this. I think you can do it in your mind, that this adds up to 100%. Okay? Like I said, in some cases, after you've rounded, it may be that you'll lose maybe a decimal or maybe 2 decimals on the total, but that's fine. If you're off the 100% by 0.5 or 0.6 or something like that, that suggests that you perhaps have a mistake somewhere. Okay, let's go back to our slideshow now.
Okay, in the previous example, we had a sample of a compound and we had its composition, and we were able to arrive at the percent composition. Now, let's say that I have already the formula of a compound. How would I predict what the percent composition is? So that if I have a sample from the field and I obtain a percent composition, I can find out, okay, is the compound that I have the same as the one that the formula told me? So the way we calculate the percent composition from the formula of the compound is we're going to take N times the molar mass of the element divided by the molar mass of the compound times 100%. What is N? Well, that's the number of moles of the element in 1 mole of the compound. Remember, if I have N atoms of an element in 1 molecule of the compound, if I multiply both the top and the bottom of that ratio times Avogadro's number, it gives me the same, the number of moles in 1 mole of molecules of the compound. So let's see if I have this compound here, C2H6O, and let's say that it has a molar mass of 46.08 grams per mole. And I gave you the structure there so you can see how the compound is actually laid out, how it's arranged in terms of the atoms. In this case, as in most cases, the black spheres are the carbons, the white ones are the hydrogens, and the red one is the oxygen. It's kind of like a conventional coloring scheme for these types of ball and stick models. Okay, so notice that in this formula we have 2 moles of carbon, and that's 12.01 grams per mole of carbon, divided by the total molar mass of the compound, 46.08, times 100% gives me 52.13%. Notice that I'm using here the sig figs that are given by the molar masses. The 2, the value of n, is an exact number, so it doesn't count towards sig figs. Okay, let me let you guys do hydrogen now. And then I'll display it. Just take a few seconds here to at least set it up. You had to look up on your periodic table what the molar mass of hydrogen is. Okay, very good. It's 6 times 1.01 divided by the molar mass of the compound times 100%. That's 13.15. Yes, I went one extra sig fig there. It doesn't matter in the end at all. Remember, at this point, I'm just putting these numbers in the calculator because I'm going to add them up later on to check something out. And then oxygen would be 1 times 16.00 grams divided by the molar mass times 100%. And the key thing here is that to check your numbers, when you finish, you'll have to add up and make sure they add up to 100%. Again, in this case, I chose to leave the hydrogen percentage at 13.15. It may be that if I had expressed it totally correctly at 13.2, according to sig figs rules, it will not add up to 100%. So depending on the rounding, you may or may not get exactly 100% total, but it shouldn't be off by more than, a few, couple decimals of a percent. If it's more than that, then there may be a mistake in your calculations. Okay, so now we're ready to put these things into place and find what is the formula of an unknown compound. This flow chart gives you a sense of how we can go. If I have the mass percent, in other words, the composition of the compound, remember that percent technically means parts per 100. So what I can do is I can convert the mass percent into grams and divide by the molar mass to find the moles of each element. Now, since the empirical formula is a ratio of the atoms of each element to each other, it is the same as taking the ratios of the moles of each element to each other. So I can divide to get the ratios per moles of the elements. And now the ratios of moles of elements to each other essentially become the subscripts that make up the empirical formula. That's a lot of words. Let's go ahead and do a practice problem. What would be the empirical formula of a compound that has the following percent composition? So pretend I got a compound, I found out a way of analyzing it, and I end up determining that it is 24.75% K, potassium, 34.77% Mn, which is manganese, and 40.51% O, which is oxygen. Remember, careful here, we're talking about oxygen, the element, right? Because this is composition, not oxygen, the molecular form of it, O2. So percent, like I said, technically means parts per 100. So let's say that I had exactly 100 grams of compound. I'm going to start by assuming that I have that. Therefore, the percent composition becomes grams in this sample of 100 grams. So how many moles of potassium do I have? Well, if I have 24.75 grams of potassium, and I use as my conversion factor the molar mass of potassium, which is 39.10 grams. Again, just like we do in dimensional analysis, the grams cancel out, and I end up with 0.6330 moles of K. Okay, why don't I let you guys try the manganese and then the oxygen. Just look up your periodic table. What are the molar masses of each? And remember that at this point, because we have 100 grams of compound assumed, each one of the percentages essentially becomes grams of that element. Cool. Okay, let's go ahead and show this. So manganese, molar mass 54.94. So the grams cancel out, and we end up with 0.6329 moles of manganese. Moles of oxygen, again, remember, we're looking for atoms of oxygen in this compound, so we're using the monatomic molar mass, 16.00. Grams cancel out, and we get 2.532 moles of O. The empirical formula is going to represent the ratio of potassium to manganese and to oxygen. So let's copy those values over here, and we have them there on the top. So since we're going to establish a ratio, we're going to express it in terms of what is the element that is present in the lowest numbers of moles. Well, just by a little bit, it would say the manganese, but essentially potassium and manganese are present for all practical purposes in a 1-to-1 ratio to each other. So let's divide everything by that. So the potassium, 0.6330 divided by manganese, 0.6329, is essentially approximately 1 for all practical purposes. Of course, manganese by itself would be 1. And the oxygen, 2.532 divided by 0.6329, is very, very close to 4. And I'll talk about that in a moment. But at this point, we are safe to round it to 4.0 units of oxygen for every unit of manganese. And so this process helps us to arrive at the empirical formula. We have essentially a ratio of, for every potassium, we have 1 manganese and 4 oxygens. And if we want, we can write it in that order. At this point, it doesn't matter. You could have written it, K04Mn or MnK04. At this point, we don't know for sure. All we know is that these 3 elements are present in that ratio. We would suspect that this is an ionic compound, but interestingly, it has more than one kind of cation, right? But further chemical analysis will let us know exactly what this is. Okay, very good. Now, we're going to do a practice exercise with another copper-containing mineral. This is azurite, which, as you can see, is used for making gemstones. And let's say that we have a way of analyzing its composition, and we find out that it has that percent composition shown in there. What is the empirical formula for azurite? We are going to do this exercise on paper because I'm going to show you something that's going to come up and a decision we're going to have to make as we analyze this composition. Okay, we'll be back to our slideshow in a moment.
Okay, we're going to try to get the empirical formula based on the composition analysis that we have here. So the problem gives us the percent of copper, carbon, hydrogen, and oxygen and asks us to get the empirical formula. So the first we're going to do is let's assume that we have exactly 100 grams. All right, I'm going to assume that we have 100. I'm going to put 0.00 grams, just make it exaggerated. In other words, out of 100 grams, then the percent, which is parts per 100, now becomes grams of that particular element. So I'm going to go ahead and write down the elements over here. Starting here on the left, I'm going to go with, first of all, I'm going to start with copper. And then I'm going to put carbon. And then I'm going to put hydrogen. and then I'm going to put oxygen. Okay, for copper, we would have 55.31 grams in 100 grams. So this is 55.31 grams of copper. For carbon, we would have 6.97 grams of carbon. For hydrogen, that would be 0.58 grams of hydrogen. And for oxygen, we would have 37.14 grams of O. So assuming we have 100 grams, the percent composition becomes grams of that element in that 100 gram sample. Now, to get the formula, we have to get moles, right? So what we're going to do here is we're going to convert all of these to moles by finding the molar masses in the periodic table. So 1 mole of copper is 63.55 grams of copper. And I'm showing all of this here so you can see how the units will cancel out. Okay, for carbon, 1 mole of carbon is 12.01 grams of carbon. And you can see how those will cancel out. For hydrogen, 1 mole of H, based on our periodic table, it's 1.01 grams of H. And so the gram units will cancel out. And finally, for oxygen, 1 mole of oxygen atoms would be 16.00 grams of oxygen, and that cancels out. So what I'm going to do now is I'm going to do these operations using my calculator, and I will adjust to the proper sig figs here. So for copper, we're going to get 0.8703 moles. For carbon, we're going to get 0.580 moles. Okay, this was copper. This is carbon. For hydrogen, we only have 2 sig figs here, so I'm going to go ahead and leave it at that. 0.57 moles of hydrogen. And finally, for oxygen, we're going to be getting 2.321 moles of oxygen. Again, we did the calculations and adjusted the totals for the proper sig figs. The empirical formula, the empirical formula is a ratio of all of these elements to the simplest whole numbers. So essentially, it's a ratio of whoever there is in there to the one with the smallest amount. And in this case, we're going to divide by the smallest one, which in this case, essentially mainly because of the rounding ends up being hydrogen. So we're going to divide everything by hydrogen. So let's go ahead and do that. We have O over H. 2.321 divided by 0.57. So that's roughly about 4.0. Carbon to hydrogen, we can see it's essentially 0.580 divided by 0.57. Yes, pretty much for all practical purposes, it's 1. Now, when we get to the copper ratio, of course, H over H equals 1. But when we get to the copper, we find something interesting. If we divide the number of moles of copper, 0.8703, by the number of moles of hydrogen, I forgot to make sure that was a 7 over there, 0.57, we actually end up with 1.5. At this point, you might be tempted to say, well, let's just round it up to 2, because 1.5 would round up to 2. Well, you can't do that. You can round up if you are within about maybe 0.1 units off of a whole number. That's okay. If this are 1.9, I'd probably be safe rounding it up to 2. If this are 1.1 or 1.05, I would be comfortable rounding it to 1. But in this case, I can't. And because my empirical formula requires that I have whole numbers, right? What I need to do is I need to convert all of these into whole numbers. So the way to do that is perhaps, right, if I could multiply this times 2, right, that would give me 3.0. But that means then that I have to multiply the whole thing times 2. And therefore, I would have copper at 3, right? And then the other ones I can write in any order I want. I'm going to go kind of clockwise here. So now carbon, which was 1, was multiplied times 2. So now it's C2, right? Hydrogen, which was 1, is also going to be 2. And then the oxygen, which was 4, we had to multiply that times 2, and we get O8. So that would be the empirical formula. I kind of like wrote it that way because I've kind of gotten used to whenever I have carbon, hydrogen, and oxygens, I write them in that order. And of course, we typically write metals first because we, on a first assumption basis, we're thinking that this is an ionic type of compound. As a matter of fact, the actual structure, the actual formula of azurite is not this, but it doesn't matter. All the question asked was for the empirical formula, and there it is. So let's move back to our slideshow.